And nobody's typing, so I'll just take it as is. What we want to do today is a whole lot of little itty bits about organic chemistry that you need to know in terms of the naming and just how we work with them and the terms we use. Then we'll go on to isomers, and all that so far is both for the exam standard as well as the internal spectroscopy standard, up to the constitutional isomers. From there, it's the exam part only. So from geometric, optical, physical properties, and so on, you won't get that in the spectroscopy internal, but you will get that in the exam. So let's start off. The first thing is, let's revise functional groups, because you do need to know this. So there are 11 functional groups you need to know. As I say, anything with halo or acyl chloride, you know there's a halogen in there. Halogen is anything in group 17. Acyl chloride, it has to have a chloride. Other little tips is in alcohol, think of the COH in alcohol, makes you think it has a COH bond. That's one way of remembering it. The amine, think of amine, Ni is nitrogen backwards, so amine contains nitrogen, and there you've got the CN bond. And the difference between an amine and an amide, they're very similar in terms of how they're named, but what is the difference? It's got a carbonyl group, a C double bond O. I'll go back up to the ketone, but what you think of is the D-amide, D for double bond, so it has that carbonyl group in it. So hopefully that'll make you not get confused between an amine and an amide. And the last one is a little tip, is the ketone. It's got an O in it, O for oxygen. Some of them you've come across at level 2, so the alkane, alkene, haloalkane, and certainly the alcohol and amine, you all came across at level 2, as well as the carboxylic acid. And the others are new for this year. Do you think you would know your functional groups based on the last lesson? If you've just come in on this lesson and you haven't done any organic before, that's a very quick introduction. So Andrew, right, so you feel confident. It's really important that you can recognize these functional groups and draw them. The other thing you need to know, and I want to revise, is the coding in terms of naming compounds, because you need to know that the way it's named, so you can either draw them from the name, or if given the diagram, that you can name it. So the end of the name is always the important functional group. So if it ends in ol, it means it's got an OH in it. So the OH doesn't have to be at the end of the molecule. It can be anywhere, depending on where we're told that's that green number. But at least the ol tells you it's got a OH functional group. The orange, the bute, tells you it's got 4 carbons in the longest continuous chain that contains the functional group. So that's the orange. The an tells you it's only got carbon-carbon single bonds. If there was an alkene in here somewhere, then this would have been butene, okay, with an en over here. And of course, it would have to have a number to tell me where the double bond is as well. So the N, if it has N in there, it's single bonds. If it's En, it's double bonds. If it's Yn, it's an ine, so it's an alkyne. You don't do alkynes at level 3 though. Just one point before we go on. If you have done CH3051 already, you may have noticed, so I'm just finding my cursor there, sometimes there's an E after the AN and sometimes there is not. It all depends what comes next. If the ol starts with a vowel, O, then we drop the E. So we never have 2 vowels together. So we don't say 3-methylbutane ol. Okay, it doesn't flow off the tongue as easily as 3-methylbutanol. Okay. If, however, my functional group starts with a consonant, so say I had 2 alcohol groups, so it's now diol. Di starts with a D, it's a consonant, so that's when you add the E. Sorry, I'm trying to find my cursor. It always disappears on me. So that's when you add the E, and then it would be 3-methylbutane, and then 1,1 diol, or whatever the second diol is. So just in case you weren't aware of that, when the E comes on and when the E gets dropped off. It's all to do with what comes next. Is it a vowel or a consonant? Right, so we've got the parent chain, we've got the functional group, and what comes next is where is the functional group. So that's in green over there. It's on the first carbon in this particular case. Then you look for side chains and you see how many carbons on that side chain, if it's a carbon side chain and not say a chlorine or something like that. Then you count the number of atoms in that side chain. So the purple shows 1 carbon, so it's methyl. Okay, the IL tells you it's a side chain. And then finally, where is that side chain? So that's a summary of cracking that IUPAC code. So if you're given the name, you can draw the compound, or if you're given the compound, you can draw it. We'll need to know this for isomers. So here's drawing the compound. So if you get given a compound, like 2-chloro-3-methylbutyrene, then you always start off by looking at what is the number of carbons in the parent chain. So but means how many carbons. If somebody can tell me the answer, but is 4, correct. So you draw 4 carbons in a row. Then you put in the functional group and you look to see where is the functional group. So ene means it's a double bond, carbon-carbon double bond, and it's on the second carbon. So if we number this as 1, this will be the second carbon. So we put in the double bond. Now we put in the side chain. So we've got a 2-chloro, so a chloro group on the second carbon, and a methyl group on the third carbon. So remember, this was our carbon 1, carbon 2, so that's where the chloro goes, and now we put the methyl in. Now, really important, this comes up always in the examiner's report, and particularly for merit and excellence. I don't know how strict they are on achieved. I don't think they are particularly strict, but certainly for merit and excellence, that bonding line tells you which atoms are bonded. So make sure that that line is between this carbon of the methyl group and the carbon of the parent chain. Don't draw it to between the carbon and the hydrogen, or from the carbon of the parent chain to the hydrogen, because the hydrogen isn't bonded to it. It's the carbon of the methyl that's bonded to the parent chain. So that is important for under particular excellence, because it always comes up in the examiner's report about sloppy drawings. So make sure you do that. And then finally, because this wouldn't even get an achieved, is that last step is fill in the hydrogen atoms until every carbon has 4 bonds, nitrogen has 3 bonds, and oxygen has 2 bonds. And of course, hydrogens and chlorines have 1 bond. So now we've completed that carbon. Carbon 2, has that got sufficient number of bonds? So carbon 1's got 4 bonds now. Carbon 2, does that have enough? Yes, because it's 2 from the double bond, plus 1 for the chlorine and 1 for the methyl. And the same thing for carbon 3, and now we've completed it for carbon 4. Just as a tip, I've got there what we could call a semi-condensed structural formula. In other words, with some of them, I've got the CH bonds drawn out, and for others, I've got like CH3. I've condensed down, I've removed the CH bonds. I really suggest doing full structural in the beginning, so showing all the CH bonds. And then as you get more confident that you're drawing enough hydrogens in and you're not giving them carbon atoms too many or too few hydrogens, then you can start condensing it. Sorry, you can condense it to a methyl, and then you could even condense it even more. You could have just said CH3, CCl, double bond C, CH3, CH3. Or you could have just simply said CH3 and then in brackets 2, if you wanted to condense it right down. But you've got to be really confident before you start condensing it that much. Any questions so far about drawing organic molecules or even naming organic molecules that we did last time? Okay, nobody's typing. So final point is, of course, check again and again that you've drawn the correct number of bonds, because I'd say that's the number one error. People leave out hydrogens or they put in too many bonds. You know, they might, for instance, over here add a hydrogen because they're thinking, oh, I've just got to add hydrogen, so they give this carbon 5 bonds instead of 4. Okay, another term we use, we talk about branched chain and straight chain. Now, straight chain does not mean in a straight line, not in chemistry. There can be lots of kinks in it because the bonds can rotate, single bonds can rotate. So don't fall into the trap of thinking if there's a kink in the parent chain, it is a branch chain, or if there's no kink, then it's a straight chain. So let's have a look. The first one is a straight chain. Now notice we're not really looking at the chlorine, we're just looking at the carbons. We want to see are the carbons in a continuous line. So we'd call that a straight chain. And the name is 1-chloropentane, and you can check your knowledge, would you have got the same? You can actually try and work out the names of all of these compounds and just check, did you match my answer? The next one is also a straight chain. So it's one continuous chain of carbons, so that would be 2-chloropentane. The next one is also straight chain. So although it looks, so I'm just trying to find my cursor, although it looks as though this methyl group is a side chain, it's actually part of this long chain, so this is also a straight chain. Does anybody want to say what the next one will be? Straight or branched? And as I say, we're looking at the carbons, we're not looking at anything like the chlorines. Nobody want to have a go? Okay. There is a part that's straight, but we do have a side chain, so we do say that that is branched because we have a carbon side chain. So if an exam, and I think this happened 2 years ago when it said, draw a branched chain secondary alcohol. I'll explain secondary just now, but that branched chain means you've got to have a carbon side chain, and it has to be like the fourth, this one over here. It can't be something like this because this is still a straight chain. The next one is also a straight chain, even though it looks as though there's a kink in it or two kinks. It's a continuous chain of 4 in a line. They could be all over the place, but they are continuous and in a line, so it's a straight chain. And the last one, does anybody want to have a go at that one? Straight or branched? Okay, one of you is going. Right, it's branched because again we've got a methyl side chain, so we say it would be branched. Do you think you could identify branched and straight chains? Or if you were told to draw a branched chain alcohol with say 5 carbon atoms in it, you wouldn't draw something like this or something like this because that would be wrong. But if you had this fourth molecule with an OH there instead of a Cl, that would be a branched chain alcohol. Okay, or if you had drawn something like the 6th molecule here with an OH here, that would also be a branched chain alcohol with 5 carbons in it. So you think you are okay with straight and branched? Okay, so one of you is. So I hope the rest of you are welcome to type in questions, or if you just want to sit and listen, that's fine, and you can always listen to the lesson afterwards. So that was 2-chloro-2-methylbutane. Why I also gave the names is that can you see the difference between branched and side chain, because you've always got that extra bit in a branch chain. You'll always have to have a 3-methyl or something ethyl, or, you know, it's not just going to be something pentane, something pentane, something pentane. It's got to have a carbon side chain there somewhere. So that the name should immediately tell you if it's branched or a straight chain. Now, I use that other terms, draw a branch chain secondary alcohol. Primary, secondary, and tertiary you did come across last year, but you may have forgotten, or perhaps you haven't done much level 2 chemistry with organic. What we're basically saying is a primary carbon atom is one bonded to another carbon atom, one other. Secondary, if it's bonded to two others, I think it's sort of self-explanatory. Secondary, second, two. Tertiary is bonded to three. Does anybody know the name if it's bonded to four other atoms, as a matter of interest? Have you come across the word quaternary before? So primary, secondary, tertiary, and then quaternary. I could type it out in the chat box over there. So you can get quaternary nitrogens, you can get quaternary, then it would have a positive charge, and you can also get quaternary carbons. Okay, so let's have a look. So my red carbon over there is bonded to one other, the blue one, so that's primary. And again, my red one here is bonded to two other carbon atoms, so it's secondary, and there's an example of a tertiary carbon atom. If it was quaternary, then that OH would have to be another carbon atom. Okay. Now, nitrogen can be exactly the same, but how many bonds can nitrogen have in total? So think of how many bonds nitrogen can form. Is it one only, two, or three, or four? Does anybody want to have a go? Sean? Three, correct. So it's slightly different for nitrogen than for carbon, because we said for carbon atom it's bonded to one other carbon atom. So if we were talking about a primary alcohol, we're looking at the OH, what carbon it is bonded onto, and then how many it is. So a secondary alcohol, the OH is bonded onto a carbon, which is bonded to two other carbon atoms. And then a tertiary alcohol would be the carbon bonded to three others. If I had a primary amine or a secondary amine or a tertiary amine, then it's how many carbons the nitrogen is bonded onto. Because an OH can only form one bond. So an OH, you know, is always, if you like, itself can only bond to one. So we always look at how many, well, the carbon atom the OH is bonded to, how many other carbons that red one is bonded to. With nitrogen, the nitrogen is a key one, so that's in red now. So it's there, it's a primary amine. The one I've just clicked on now is a secondary amine, because it's that nitrogen is bonded to two others, and then tertiary amine, it's bonded to three others. Then a quaternary amine would be, and you won't come across this, but just so that you know, if there's another carbon bonded to that, and that can happen in organic chemistry, and then it would have a positive charge. So, are you clear with branched and straight, and primary, secondary, and tertiary? Okay, Sean, right, good. Okay, there are things you came across last year, but it's important things you need to know again this year. You will be asked to name primary amines in the exams. You will be asked to recognize secondary and tertiary amines, but you wouldn't be asked to name secondary and tertiary amines, because the naming is slightly different. Instead of using a number, you use N. And that can be confusing if you're not used to it. Okay, so let's do some practice. So number one, now we're looking, is this, and we've got chlorines in all of these cases, so haloalkane. Are these haloalkanes primary, secondary, or tertiary? So number one, is it primary, secondary, or tertiary? You can just say 1, 2, or 3. Primary. Good. Number two, is it a primary haloalkane, secondary, or tertiary? So you look for the Cl, you look for the carbon that it's bonded to, and then you see how many other carbons has it been bonded to. I'll just show you with that. So that was the primary, it was bonded to one other one. Now, okay, I see Andrew's typing. Okay, stop now. Right, so that was a primary 1-chloropentane, and it's a secondary because there's my CCl. So as I say, we're focusing on that carbon the Cl is bonded to. It's bonded to two others, so it's secondary. The next one. So look for the CCl. Is it primary, secondary, or tertiary? Anybody want to have a go? Right, primary, because there's the CCl, and that is only bonded to one other carbon atom, so it's primary. And the next one, there it is. So is that primary, secondary, or tertiary? Does anybody want to have a go? Thanks, Andrew. Right, it is primary again because it's only bonded to one other. And so there's our CCl for molecule number 5. Is that primary, secondary, or tertiary? Secondary, because it's bonded to two others. And finally, the last one, is that primary, secondary, or tertiary haloalkane? Nobody want to have a go? Yep, okay, Andrew, correct. There's 3 there. So as I say, it's branched and straight, then it's primary, secondary, and tertiary. You do need to know those terms. And there's the name for that compound. You can always check your naming, so I hope you got the same names. Remember the hyphens between the number and the letters, so it's 2-chloro-2-methyl butane. No spaces between the methyl and the butane. Okay, now this is another thing you need to know, so it's the third little bit of information you need to know, is the degree of unsaturation. And last year when you did alkanes, alkenes, and alkynes, you were given some formulae. CnH2n plus 2, CnH2n, and so on. So we use that to work out the number of possible bonds. So unsaturated means that the carbon atom does not have 4 atoms attached to it. Now, notice I didn't say 4 bonds. It always has 4 bonds, but if it's unsaturated, it still has 4 bonds, but it has less than 4 atoms. So as an example, I've got there an alkane, alkene, alkyne, and in an alkane, each carbon atom has got 4 atoms, as well as 4 bonds. And if you count there, I've got 2 carbon atoms in that alkane, ethane, and I've got 6 hydrogens. So if I make the N for the number of carbon atoms, if it was 2, 2 times 2 is 4, plus 2 is 6. So I have got here 2 carbons, 6 hydrogens. It obeys that formula, CnH2n plus 2. This ethene is 1 double bond is present there. Okay, it's unsaturated because each carbon of that double bond is, although it's got 4 bonds, it's only bonded to 3 other atoms. So each carbon is bonded to 2 hydrogens and 1 carbon. So the formula there is CnH2n. If I think of each carbon, I've got 2 of them, so it's 2. And if I multiply that by 2, I get 4, and I've got 4 hydrogens. So that's how we get that formula, CnH2n. Who wants to have a go at the last formula? So we know it's very unsaturated because we've only got 2 atoms bonded to each carbon. Would anybody want to have a go at the formula we can come up with? So if we had Cn, what would the H be? Nobody want to have a go? Okay, if you had CNHN, then fine, that would work for a small molecule. Okay, I can see Jonathan is typing, but I'll just put it in. We can't have something with lots of triple bonds going in a row, so we could have a triple bond bonded to a CH2 to a CH3, so we still have the CNH2N, but then we have to remove two hydrogens because they were removed from here. I mean, if you think of, if I remove this hydrogen, that hydrogen, and put another bond there, I get the alkyne. So this formula applies for a single triple bond, or, because you don't do alkynes, it could be two double bonds as well. Okay, so let's have a look at if we have other elements present, not just carbon and hydrogen. Oxygen doesn't affect the ratio. So if I had C4H8O, the oxygen doesn't affect the ratio at all. It still follows at CnH2n plus 2 or CnH2n or CnH2n minus 2. Fluorine, chlorine, bromine, and iodine, the halogens, they're included with hydrogen. So I add them up with the hydrogens. Nitrogens, what happens with them? Because nitrogen can form one extra bond, there'll always be an extra one. So what I'm trying to show here is if I have an amine and it's a saturated compound where every carbon and every hydrogen has got the right number of atoms bonded to it, then it'll be CnH2n, and instead of 2n plus 2, it's now 2n plus 3. So if you have a look here, it's 2 carbons, so N is 2, and I've got 1, 2, 3, 4, 5, 6, 7. So 2 times 2 is 4 plus 3 is 7. Does that make sense? Okay, right, so we'll see how we go with this one. If we have a double bond here, then if we count, I've got, if N is 2, then if remembering that nitrogen always allows one extra hydrogen, so I should expect 2 times 2 is 4 plus 1, I expect 5 hydrogen atoms, and you can see that here, 2, 3, 4, 5. And then finally, if I have 2 double bonds, then the formula is CnH2n. Instead of minus 2, it's now minus 1. So again, if it was 2, 2 times 2 is 4, minus 1, so it's 3, and there you go. I've got 2 over there, plus 1 is 3. So you will need this for the spectroscopy standard, as well as for the exam. Sorry, is there a lot of noise around, or are you hearing me? Because I'm hearing a lot of noise around me. Okay, Jonathan and Sean might see are typing. Okay, you can hear me fine, great. It's just we have to move tomorrow, so we're busy packing up. Okay, so let's hope you remember those formula of CnH2n, CnH2n plus 2, CnH2n minus 2, and of course when we use the oxygens, the hydrogens, and the nitrogens. So, number 1, how many... okay, I see that the here and the here. Right. How many double bonds are present in the first molecule, C3H6? Somebody have a go. Guess if you have to. That's always I tell my students. Don't leave anything blank, always guess if you really don't know. Okay. 2 double bonds, 1 double bond. It's actually 1 because remember it's CnH2n for an alkene. So 1 double bond. So it just follows that formula, CnH2n. The next one, is that CnH2n or is it CnH2n plus 2? or CnH2n minus 2. So basically it's an alkane, an alkene, or an alkyne, or two double bonds. It's okay, somebody was typing there. Does anybody want to have a go? Okay, Jonathan, I saw you were typing. That follows the formula of CnH2n plus 2. Because if you think, if n is 4, 4 times 2 is 8. So to get to 10, I have to add 2. So can you see it follows the CnH2n plus 2? And that's the same as an alkane. So an alkane doesn't have any double bonds in it. So it's 0. How about the next one? C3H8. Think of what formula does it match? Is it CnH2n? Are there double the amount of hydrogens to carbon? Are there more hydrogens than carbon? Lots more, like 2 double plus 2, or is it double minus 2? Okay. It's an alkane, correct? So it'll have 0 double bonds in it. Now here's a case where I've got a chlorine. Now remember what I said, a chlorine, any of the halogens, you have to add it on. So I've got 7 hydrogens, but I've got 1 chlorine. So it's as though I've got 8. So this formula is C3H8, exactly like that one. Because the chlorine is like another hydrogen added on as far as working out the number of double bonds is concerned. So would you expect this to be the same? Do you think it'll be 0 double bonds? Because it follows the CnH2n plus 2, yes. Okay. Here we've got something where we've got an oxygen in it, in the molecule 5. Now remember what I said about oxygen. Oxygen has no effect. You can just ignore the oxygen as though it wasn't there. So we're just focusing on the C2H4. So if I just focus on C2H4, are my hydrogens double the number of carbons, so 1 double bond? Is it double plus 2, so it's no double bonds, or is it double minus 2? So in other words, is it no double bonds, 1 double bond, or 2 double bonds? Anybody want to have a go? No? Okay. It follows the CnH2n formula because 4 is double 2. So 2 times 2 is 4. So C2H4 is CnH2n. Remember I said ignore the oxygen. Now here we've got a nitrogen. So nitrogen is a bit tricky because you've got to learn those other formulae. So you've got to think, is this double? I've got C3. So double 3 is 6. Now remember with the 6, that would have been straightforward 1 double bond. But because I've now got a nitrogen in it, you've got to say, does it follow CnH2n plus 3, or CnH2n plus 1, or CnH2n minus 1? Sorry, CnH2n, yeah, plus 1. Yeah, the plus 1 one. So it has the 1 double bond, correct. And here is one where I've got C5H11ON. Remember the oxygen we just simply ignore. That's not part of the formula, ignore it. It has no effect. The nitrogen does. So you've got to think of, okay, that 5, if I double it, it becomes 10. So I've got 1 more. It's at CnH2n plus 1. The same thing as we had over here. So I'm going to have 1 double bond. What I've got over here is C6. Now if I doubled it, it would get to 12. So it looks like an alkyne. It's got 2 less. But remember, I've got chlorines in there. So I've got to add the chlorines to the hydrogens. So I've got 12 in total. 10 plus 2 is 12. I ignore the oxygen. So C6H10 is now C6H12 because I've included the hydrogen, the chlorines. So how many double bonds have I got now? 1, correct. And let's look at the last one, C4H5OCl. The oxygen we can ignore straight away. The 5, we now have to add on the chlorine to it, so it becomes 6. C4H6. How many double bonds have I got? So you've got to think, does it match CnH2n plus 2, CnH2n, CnH2n minus 2? The minus 2, which means I've got 2 double bonds. So the double bonds, remember, don't have to be alkenes. It could be a carbonyl group with an alkene. It could be 2 carbonyl groups. It just means somewhere in the molecule I've got 2 double bonds. Okay, so this could be, for example, an acyl chloride that accounts for 1 double bond, as well as an alkene in here. Okay, so we're going to be looking at that now with isomers, where you get given a formula and you've got to try and work out what structures you can draw from it. So, revision from last year. Isomers are molecules that have the same molecular formula. That's really important, but the atoms are just arranged differently in space. Okay, to change from one isomer to another, I have to physically break a covalent bond and remake it elsewhere. So here's an example where I've got a carbon, it's 4 carbons in a row with an oxygen, so it's butanol, a butanol. If I place it on top of each other, it looks as though they're different, but if I flip it around, then can you see it's exactly the same molecule? Are those 2 things isomers or not? No, because they're totally superimposable. They're exactly the same. And one way of working out whether you've got the same molecule or not is to write the name out. And in both cases, it's butan-1-ol. Let's do another one. Okay, I think you can see that these are isomers because I've got butan-1-ol on the left-hand side, sorry, on the right-hand side, and my OH is not on the first carbon over here. But if I moved it across, again, it doesn't look as though it's superimposing, just like the first time. And if I flip it around, there's no ways it'll ever match up. And to try and make them match up, I actually have to, sorry, I flipped it back there, I have to break that bond, put it so it superimposes, and do the same thing with the hydrogen. I haven't bothered with that. So that's the difference between drawing the same molecule and drawing an isomer. To change from one isomer to the other, you've got to actually break a bond. So, last year you only had constitutional isomers and stereoisomers. This time we're going to have, and geometric isomers. This time we're breaking the stereoisomers down to 2 different types, geometric and optical. So first of all, remember what I said, molecules have the same molecular formula, but they're arranged differently in space. That's an isomer. A constitutional isomer, also known as structural, it's when the atoms are joined in a different order. So they're connected differently. Okay, they have a different connectivity. We might bond 2 carbon atoms and then an oxygen atom, whereas in its isomer we might have bonded 1 carbon atom, then the oxygen before we do the second carbon. So they're just joined in a different order. Stereoisomers are where the molecules are arranged in the same order, okay, like 2 carbon atoms and then the oxygen, but where those atoms are in a different position in space. And I think you'll remember that from geometric isomers, but we'll go over it again. And then we've got a new type called optical isomers, or enantiomers, that we'll look at. But let's go over the constitutional first, because this is what you're going to be needing also for the spectroscopy standard. The constitutional isomers, because we're just taking the atoms and just bonding them in different ways, we can land up with different functional groups. Or we could have the same functional group, but they're on different parts of the chain. Is it on carbon 1 or carbon 2 or carbon 3? We could have varying lengths of the carbon chain, so we could have, say, 5 carbons in a row, like pentane, or we could take one of those carbons, so we've only got 4 carbons in a row, and make one a side chain. Okay, and then we can put those side chains in different positions. So those are all the different ways we can make constitutional isomers. So let's put all that knowledge we've put in about our number of double bonds into place, and then we're going to think of what functional groups we have. So if I give you C3H70N, how many double bonds have I got in that molecular formula? So is it CnH2n plus 3, CnH2n plus 1? Okay, it is plus 1. Sorry, yeah. Have I got by CnH2n plus 3, and then it's, sorry, I've got a wrong formula there. That is not minus 1. Sorry, my error. That is supposed to be CnH2n plus 1. Because C3 double it becomes C6, H6, and I've got H7 there, so it's plus 1. So please accept there's an error over there. So I've got the CnH2n plus 1, so I've got 1 double bond present. If I've got 1 double bond present, what sort of functional groups can I have in that, can I make from that molecular formula? Does anybody want to have a go? Okay, I'll just write that down. There is one. I've got a alkene for the double bond. I've got my O as an OH, and I've got an amine. So that's one way I can draw a molecule with an amine, an OH, and a double bond. Or I could make a ketone. So a carbonyl, correct, and there's various carbonyls we could do. So I could make a ketone, so that it uses up my double bond straight away in the carbonyl, and then I could have an amine with it. Or I could have an aldehyde with an amine. Or I could have an amide. So here's an example of an amide. So my N is being used up, my O is being used up, and I've got a double bond. So here's some more. Here's where I've used my OH plus alkene plus amine, but can you see what I've done is I've moved the functional group to a different position. Here it was on C2, and now I've put it on C1. And here's an example of an aldehyde. Oh, and then, so there would have been more you could have drawn. So when you look at a compound, work out, or a formula, work out how many double bonds can I make, and therefore what sort of functional groups are involved. So let's have a look at this one. C4H8 oxygen. And what can we do? So first of all, as I said, you look at the ratio. And you get an aldehyde, a ketone, or an alkene alcohol mix out of that. Okay, now these 4 different steps, sorry, 6 different steps, I'll repeat again, but it's basically you draw your carbon atoms in a row, just like in drawing a compound, draw the functional group, and then you just keep on moving that functional group along until you get a repeated molecule, and then you try it with a different functional group, and so on. So those rules will come up again, there they are, and now we'll go step by step. So 4 carbons in a row, 1, 2, 3, 4, and I've decided to do the aldehyde first. So on carbon 1, I draw the aldehyde. And naming it really helps to work out whether you've got a double or not, you know, if you made an identical molecule. I don't have to put the 1 in for butane 1L, because remember, an aldehyde is always got to be at the end of a molecule. Say now I move that carbonyl group, sorry, where's my, so I move that to the last carbon. Okay, so can you see I've shifted it to the last one, because we know it's always got to be at the end, an aldehyde, we can't have it in the middle. Have I made a different molecule, or have I made the same molecule? And the way to work it out is name it. And if you come up with the same name, it's the same molecule. So is that the same molecule or different? So I can see Andrew's typing there. You sure it's different? Because here we have to remember the functional group always has to have the lowest possible number. So in this case, it's carbon 1, 2, 3, 4. And then over here, we can't start on the left-hand side anymore because the functional group has to have the lowest possible number. So it's 1, 2, 3, 4. So it's butanol all over again. That's why we did the naming of the compounds first, so that you know how to name. But I know we are moving through this quite quickly. So I'm going to cross that out because it's the same molecule. Now I'm going to do the next step, which is number 4. You do the same thing, but you make the parent chain shorter and you put on side chains. So I can actually take those 4 carbons and make it just 3 with 1 side chain. And that will be then 2-methyl propanol. I can't move that onto this carbon because this carbon already has got 4 bonds on it. So I can't make it 1-methyl propanol. And I can't move it onto the last, so I'm trying to see my cursor there. I can't move it onto this last carbon because then it just simply becomes butanol again. So that's as many isomers I can draw for an aldehyde, 2 of them. But I can do another functional group, and that's a ketone. So remember, ketone can never be on the end, it's got to be in by at least 1. So that's butan-2-one. And if I moved it to the next carbon, would I get the same molecule again? So there I moved it to the next carbon. So remember, your functional group always must have the lowest possible number. Is that the same molecule or different? Same, correct. And there's the same name, so we can cross it out. Okay, I see the time is going a bit quickly, so I'm going to move fairly quickly through this. The lesson is being recorded, you can watch it again and just see how you get through it. So here I've done what I've said you shouldn't do over here, where I've moved the methyl onto the end carbon, I've moved the methyl onto the end carbon, but remember although it looks as though I've got a branch, it isn't, it's still a straight chain, 1, 2, 3, 4, it's still butan-2-one, it's not an isomer, so there you go. So aldehydes and ketones, that's the only isomers I can draw for C4H8. But we can still do the hydroxyalkene mix or the alcohol-alkene mix. So there's my 4 carbons in a row. OH, I'm going to start with OH and the alkene both on carbon 1. Now I just move the OH to carbon 2. And then I move the OH to carbon 3. And look at the names. The names are always different, so it's a different isomer. And do you notice, because the hydroxy is always a dominant functional group, although this was carbon 1, carbon 2 in this molecule, over here I have to start carbon 1, carbon 2 to give it the lowest possible number, and that's why the double bond has suddenly gone up to 3. And then I moved my OH right down to the end, and I've still got a different molecule. Now I move my alkene along, so I've moved my OH back to carbon 1 and I've moved my alkene along, and I can't move the alkene along anymore from this because then I go back to but-3-en-1-ol. Okay, so I've got but-2-en-1-ol. So what I'm just doing now is moving the OH along, but-2-en-2-ol, and you can see none of these names match. So here I've tried a different one. I've tried to put a side chain on, but can you see it's the same name, so not a different isomer. And there's only one other isomer we can draw, and that's a 2-methyl but-1-en-1-ol. So you can see there's a side chain because of the 2-methyl. So that looks quite complicated, but it's just, you just need to be systematic and move things along and write the name to check whether it's something different. And if you come up with the same name, then you haven't drawn a different isomer. Okay, so I think we'll still have time to do the other isomers, so let's go through it. Geometric you came across last year. And it's really a geometric isomer is when we have a double bond, a carbon-carbon double bond. Please state carbon-carbon, because you know you've got a carbon-oxygen double bond and a carbonyl. So if you just say double bond, the teacher will say, which one did you mean? So please be clear, carbon-carbon double bond. If we don't have a double bond, so if we look at this bond over here straight on, that's what I'm trying to show in this over here, we're looking straight down that bond. Being single bonds, they can rotate. Okay. If I look straight down a double bond, so that's what's showing over on this right side, I'm looking straight down the double bond, it can't rotate. The bonds won't allow it. It's fixed. It can vibrate a little bit. All bonds can vibrate a bit, but that's about as much it can do. And because of that, can you see, although in this carbon I've got a bromine and a hydrogen attached, and I've got a bromine and a hydrogen attached. So I've got the same molecular formula, the same connectedness, a carbon atom with a bromine hydrogen and double bond, and a carbon with a bromine hydrogen double bond. If I take this bromine, so I'm trying to find my cursor, if I take this bromine and put it up here, swap these around, will I get a different isomer? Will it be the same? Sharma's typing. Okay, it actually won't because of that carbon double bond restricting the rotation, because I can't flip it back again. So what we need is just simply, for a geometric isomers to occur, is that A must be different to B and C must be different to D. And I strongly suggest in the exam, just write something like this out when you're trying to explain geometric isomerism. Diagrams tell is worth 1,000 words, so it's much quicker doing it like this. I can have A equal to C, and I can have B equal to D, or B equal to C. That's not a problem, but A and B must be different, and C and D must be different. Because if I have those differences, and here they are, okay, I cannot ever make this cis form that trans, because this rotation is not allowed, so the BR I can never drop down to, or this BR I can never drop down to there. I have to physically break this bond and physically break that bond to, and then remake them in the new position. So that's what we mean by stereoisomerism, where we have the same molecular formula, the same connectivity, but the atoms are arranged differently in space. And one way to remember the cis is if you put it on its side and you go from, you could have done the same thing for the hydrogens, but just because the C went this way, if I go from one big group to the other big group and it makes a C alphabet, then it's cis. Otherwise, same side, cis. Think of the sound, same, cis. That's another way to remember the difference between cis and trans. Okay, so that's what you did last year, so I don't want to spend too much time on that, because when you go through the booklets, it should be okay. The other one is the optical isomers. Now, with the optical isomers, it's again, we've got the same molecular formula, the same connectivity. So our carbon, our atoms are bonded in exactly the same connected order, but they are arranged differently in space, just like the geometric ones. But here we do not have a double bond. What we need here is a carbon atom with 4 different groups on it. So it has to have 4 different groups on it. And that's what we call an asymmetric carbon. Not an asymmetric molecule, an asymmetric carbon, if it's got 4 different groups on it. Another name for it is called chiral carbon. It comes from the Greek word meaning hand, because if you think of your hands, you can't superimpose your hands on each other. You can match them up, but you can't superimpose them, put one on top of the other. Your thumb is in a different position to your other hand. So that's where that word chiral comes from that Greek word. And your hands are mirror images. So optical isomers or enantiomers are mirror images of each other. So what this diagram is trying to show here is, can you see I've got a matching square hole here, a matching circular hole, and a matching triangular hole here. If I swapped these around, so if I made this blue block and the orange triangle swap around, can you see the triangle won't match in the square anymore, and the square won't match in the triangle anymore? So they're different. And this is very much how your body works. Your body works on chiral compounds. So that's the way you taste something. Why? Because your particular compound will lock onto your taste bud in a certain way, and so trigger a certain nerve. And they'll say, it tastes like caraway. And exactly the same molecule, but a different enantiomer, will make it taste like mint. So it'll have a totally different taste because it locks in differently. So your body is very much into chiral compounds. Okay, so remember what I said, it's got to be, the molecule must be asymmetric because the carbons have to be asymmetric. The carbon must have 4 different groups on it, and it's called chiral. And always identify that chiral compound when you're asked why something has got enantiomers. It shows you've understood what it is instead of just simply repeating a list like over here. So say the chiral carbon is C3 or the chiral carbon is C2. Okay, and the molecule is also chiral as well. So if I take those two, and you can see they are not superimposable, I can try and turn it around, but there's no ways. I've now made the green match up and the red sort of match up, but the methyl groups are not matching up. So those are enantiomers. So what are the properties? First of all, because they're pretty much identical, they've got the same melting point, the same boiling point, the same density. Everything is absolutely identical. The only thing where they're different, and I'm just going to flick through that because I mentioned that, is that last bit over there is if I put it into a polarimeter, then the plane of the polarized light will change, will be turned in opposite directions by the same amount. So what is a polarimeter? It's basically, you've heard of, does anybody wear Polaroid sunglasses? Nope? Okay, because if you did, you could try this on your cell phone or your computer screen. Because the light coming off a computer screen or a cell phone screen is actually polarized. So if I've got two polarized plates, what happens, it's like a thin crystal so that the light can only vibrate in one direction. So what I'm trying to show here is the light is vibrating in all directions from this light source. But if I put it through a Polaroid lens, or like the light coming from a computer, it vibrates only in one plane. Okay, and as it passes through a solution of an enantiomer, that light gets turned more and more and more. So the longer the tube, the more it turns the light. So whenever we quote by how much it turns the light, we always have to give the concentration and the length of the tube. It's normally always 10 centimeters. So it vibrates it, and then the analyzer looks at the angle in which it has been turned. So very briefly, I'm going to show this, and then most probably we're at our end. I'm going to take it from 25 seconds. So what can you see? Those are two Polaroid sheets. So can you see how it blocked off the light? So what they're going to do now is, and I'm just going to hurry it on a bit. So they're going to take glucose, which is a chiral compound. Remember, I said your body is full of it. And they're going to put it on here. So it's polarized light coming through in one plane, and they're putting another analyzer on top, or another Polaroid sheet on top. And then just now they're going to look at it. You can, if you just go YouTube, Farnborough Chemistry, okay, can you see they're rotating the plane, but can you see the light still coming through? And can you see the rest of it? It's gone dark, but that's light. And now it's rotating a bit more, and that's gone dark, and the rest has gone light. So it has bent it a little bit. It's changed the plane of the polarized light. So that's what I mean by that. Okay, We've got a minute left, so let's go. How do we draw enantiomers? I know I'm rushing this a bit, so please next lesson ask questions. You will get asked to draw enantiomers in 3D. It's guaranteed. Okay? So one way of drawing it, method 1, draw it because bond angles and tetrahedrals about 109 degrees, so approximately 110 degrees, draw those two lines. Then draw a solid wedge coming out with the thin end closest to the carbon and the thick end of the wedge sticking out. Make it round about a right angle, okay? And then you do the other thing, right, just a little bit above that wedge, make a hatched wedge where the thick end is closest to the carbon and it sort of trails away. We're trying to show this is sort of in the plane, this is sticking out of the plane of the paper, and that's going behind the plane. That's all what we're trying to show in 3D. And then you simply add the atoms of where you want them to be. So that's method 1. If you think that's too complicated with your angles, because I find some students really struggle in getting angles correct, because it has to look like a 3D molecule, it can't be weird. So this might be a more suitable method, because it's only right angles involved. So draw the carbon and draw two wedges sticking out on either side. Doesn't matter if it's up or down or horizontal. Thin end closest to the carbon. You want to show those bonds coming out of the paper. Then you show just at 90 degrees from them, but you're showing this hatched edge where it's thickest close to the carbon and it's trailing away behind the paper. So if you draw it like that and you add the atoms, that's a very easy way to draw a 3D molecule. Okay, to draw the second enantiomer, the mirror image, you simply swap a pair. And I think I'm going to stop there